Hello, everyone. Thanks for coming. I'm Jason from Intel Corporation. Very glad to have this sharing to introduce our team's work. Today, this topic is about an approach to system upgrade. We hope it can benefit some usage scenarios, especially for cloud vendors. When we talk about the system upgrade, we face some headaches. The first one is that nowadays we are seeing more and more frequent security fixes. Those security fixes are not coming from the OS side. It can also come from firmware, microcode, and other parts of the system. So we have to do more frequent system upgrade nowadays. And another issue is that usually the system upgrade involves system reboot, and the reboot has a pretty long time to finish. So as a consequence, the cloud vendor sees more service downtime to their customers. Of course, we already have some mitigation solutions. One is the live patching. The other one is the VM live migration. They all have their advantages, but also they have their limitations. For live patching, it is good for small fixes because there is no service downtime. But when the changes are becoming bigger, then the failure rate are becoming high. For live migration, it is a major feature in most hypervisors, I think. And it typically has a less than 1 second service downtime. But it also has limitations. For example, it does not support pass-through device very well. And it is not very friendly to memory-intensive workloads. Besides this, it also requires space machine to migrate the VM into. Also, live migration will involve some infrastructure configuration changes because we have to migrate VM to another machine. So the infrastructure changes, the network, for example, the network configuration change may impose some failure cases. So we have another approach, with just another approach. We name it VMM fast restart. The main idea is to leverage kexec reboot to bypass firmware boot phase, which will make the reboot very fast. And also, we try to put the guest state, the guest memory, totally in the system memory, because kexec reboot does not power cycle the machine. So after the kexec reboot, the guest VM memory state are still there. We can just pick up the memory state. We also want to support pass-through devices. So the main goal is to make sure the pass-through device is still working during the kexec reboot. Keeping them working means that we will need to keep the DMA, IRQ, and such things also alive. So we want to keep the DMA and the IRQ hardware resources intact during the kexec reboot. And after the kexec reboot, the new kernel will boot up and then pick up the hardware DMA and IRQ configurations so that the resumed VM can run continuously. So we hope this is a new option for some use scenarios, especially for the case that only OS and hypervisor upgrade is only needed. If the firmware or microcode also need to be upgraded, then that would be another story. So we expect this approach will have some benefits. The first one is that because we do have a reboot, so we expect it will have a higher success rate than previous approaches, especially the live patching. And we also want to have less impact to the guest OS. Although we will have, because we have rebooted the machine, we may have some relatively longer downtime than the previous approaches. And most importantly, we want to support pass-through devices. So let's dive into the technical details a little bit more. The first question is how we put the guest VM state in memory. The basic idea is to reserve most of the host DRAM memory and then make it to be emulated as a persistent memory. DRAM emulate to PMEM is an upstream feature. So the code is already there. There is no change. There is no need to change the Linux. And also, after we reserve the persistent memory, we make it to be a persistent memory block device, and then create a file system on the persistent memory. And we also mount it in a DAX mode, so that when we launch QEMU, when we run the guest VM, we run it in place in the persistent memory. So there will be no page cache, and page cache involved. So when save and restore the VM, there is no need to copy the guest memory from memory to the file system. So in this way, we have a simplified memory model. There's no need to modify the Linux memory management subsystem. And naturally, because the kexec reboot does not power cycle this machine, the persistent attribute makes the VM state stay in memory after reboot. So another issue is how do we save and reloading the VM state across before the reboot and after the reboot. We leverage the snapshot mechanism from QEMU. Basically, we customize the save VM and the load VM command or option from the QEMU to achieve an optimized or special snapshot. Because we have been running the QEMU in the DAX file system in place. So we don't need to copy the guest memory to the disk snapshot. We just keep it in the memory. For non-memory state, they can be either in disk snapshot or just in memory. The storage is special. We just flush it before we stop the VM. So when relaunching the QEMU, we will pick up the guest memory from the DAX file system directly and remap it into the QEMU and relaunch the guest. So saving and reloading involves a kexec reboot in between. So we have to pass the information where we have reserved the DRAM memory for the guest, such information to the new kernel after kexec. We use the same memory map Linux kernel boot parameter between to pass such information from old kernel to the new kernel. And pass-through device support, we think it is the most challenging part from our view. The main goal, one of the main goals of our approach is to support the pass-through device. But as we know, there are bad news and good news for pass-through devices. The bad news is that from host side, we don't have much control on the device hardware state because it is managed by the guest VM driver for the pass-through devices. So it is hard for the host to do suspend and resume of the device, pass-through device without hardware support. The good news is that unlike live migration, we don't move the VM to another machine. So we don't need we don't need to save the hardware state machine or device hardware state from one machine to another machine and restore it, because we are running on the same host. So we don't need to have hardware support for the device state. And we also don't need to have the dirty page checking from the pass-through devices. So naturally, we are taking the approach that just keep the pass-through device alive during the kexec reboot. So because the kexec reboot will involve the new kernel boot up, and new kernel will re-enumerate the device and will re-initialize the devices. So if we want to keep the device alive, then we will need to avoid clobbering the hardware state of the pass-through devices. And also, we want to keep alive the pass-through devices. We also need to keep the upstream devices of the pass-through devices alive, including IOMMU and PCIe switch or root ports, etc. After reboot, then the software side will need to pick up all the hardware configurations and then resume that VM. So for interrupt, there's an issue with the interrupt, because when we do kexec reboot, the CPUs are undergoing the reboot. They are not available to respond to the IRQs that triggered from the IOMMU or pass-through devices. So the approach we take is to leverage the posted interrupt mechanism. The basic idea is that there is a suppression notification bit in the posted interrupt descriptor. With this bit set, then the IOMMU will not send a notification interrupt to the CPU. So we can achieve the goal that we don't bother the CPU when the pass-through devices have interrupt. And at the same time, the IOMMU will record the guessed IRQ in the posted interrupt descriptor. In this way, hardware will continue using the old posted interrupt descriptor and interrupt remapping table entries for the IOMMU, and the device can still triggering an interrupt, but the interrupt will not reach to the physical CPU. It just recorded in the posted interrupt descriptor. After reboot, then the KVM and IOMMU will reuse such kind of hardware resources to reconnect between the software and the hardware. Similarly, DMA part, we just keep the IOMMU configuration intact during the kexec reboot. The hardware continues using the old page table in the memory, so DMA can go on during the reboot. And after reboot, the IOMMU driver will pick up the page tables. There are also some special handling for the kexec reboot processing. Because currently, before the kexec reboot, it will call the driver's shutdown callback. So we need to skip shutdown of pass-through devices and its upstream devices before kexec reboot. And we also pass some information, pass some data from old kernel to the new kernel. For example, the pass-through device list and memory occupations. For example, the IOMMU allocates page tables. Such kind of memory occupation need to be passed to the new kernel, and the new kernel will need to reserve it to avoid allocation to other parts of the new kernel. So we may need to extend the boot protocol. And during the new kernel boot up, there is a device enumeration phase and driver matching phase. In this phase, we also need to avoid attaching the native driver for the pass-through device. We have to reattach it to the VFIO driver. For the upstream devices, IOMMU and the switch port, something like this, then they will need to pick up the hardware state and avoid clobbering the hardware state. We also need to reassign the device to the guest. And the reassigning procedure is a little bit different than the normal assignment. So during the reassignment, we have to skip the reset and the PCI initialization. We also leverage the snapshot mechanism that we mentioned earlier to save and restore the internal states of the VFIO driver, including the MSI and MSIX state and the DMA mapping. So we complete the reassignment in two phases. Firstly, the usual VFIO realize will reattach VFIO groups, domains, etc., but without hardware clobbering. We then, at the stage of snapshot reloading, we reconnect the DMA mapping and the IRQ state according to the VFIO internal states. So to achieve this, we may need new IO control comment or flags to indicate this is a reassignment. Or the VFIO driver can handle this automatically by recognizing the device is in a pass-through device list. So this is a recap of the whole high-level flow. The left side is running in the old kernel. We first start VM and save snapshot in memory and record hardware resources, including memory resource occupation, and then trigger kexec reboot. When the new kernel takes over the control, it will do device enumeration. Then in this phase, it will avoid hardware clobbering and avoid native driver attaching. Then the upstream devices driver will need to reload their state. After that, the VM can be relaunched, and its snapshot will be reloaded from the DAX file system. And at the snapshot reloading phase, DMA mapping and the MSI and MSIX state will be restored. So there are still some opens, actually. For example, how we handle trusted reboot. Can we trust the information passed from the old kernel? And another issue is that how do we resize memory when the configuration changed? And the third open, maybe, do we want to support SIOV? Usually, we assign VF to guest VM. But for some specific devices, there are communications between VF and PF. So in this way, we may have to some way to save the state of the PF and restore the PF. But such kind of state saving and restoring is totally device specific. So this is the opens. And here is the current development status in our plane. We split the approach into 3 milestones. The first one is with do the VMM fast restart without pass-through devices. This has been done. And the second part is to not reboot the host, but just restart the QEMU with pass-through devices. In this milestone, we will exercise the DMA and IRQ detaching and reattaching. So this milestone, POC already have done. And the third milestone is to implement the full-fledged VMM fast restart with pass-through devices and with host reboot. This is going on. Next step, we hope we can upstreaming this effort. So we need your help and we need your comments. Thanks. This is our presentation. Any question? Thank you.
Thank you for your talk. When you keep the I/O memory mappings alive, how do you prevent the kexec kernel from stomping over them?
There will be some modification in the IOMMU driver. So when the new kernel boots, when it reinitializes the IOMMU, it will notice and will pick up corresponding hardware configuration.
No, I mean the EPT page tables for the devices. They're lying somewhere around the Linux memory, right?
Yes, those information are passed from old kernel to the new kernel. So the new kernel will not reserve such memory region for the IOMMU usage.
Okay.
Yeah, the page tables. Yeah.
Thanks for your talk a lot.
Thank you.
I wonder how often do you realize that the new kernel is not compatible? Well, the new kernel cannot handle the kexec, and you decide to go through the whole host reboot instead of using kexec, even though the firmware upgrade isn't required. And how do you make this decision? Thanks.
So you mean?
Yeah, how often the new kernel cannot handle the kexec and you go through the host reboot? Or is it always the case when, if you need to upgrade the kernel, you do kexec?
You apply the new kernel, right?
Yeah.
Set up the boot.
Yes.
Yes, and yeah, we can run a kexec command to load the new kernel into memory and then jump to it to
yeah, I understand. I mean, for example, if you upgrade from 4.14 up to 5, is it always the case when you can follow this approach? Yeah. Awesome. Thanks.
There are some updates for which you won't want to do that. If you need to update the BIOS, sometimes you need to reboot the host. But generally, for a software update, yeah, you can just kexec into the new kernel and it keeps going. So in one of your early slides, you had the time. I think you said this method would take about 10 seconds?
Yes.
Where did you get that number from?
The 10 seconds is mostly the out-of-box data that we gathered without hard tuning of the reboot. I think it is possible to achieve several seconds after some optimization for the kexec reboot and with specific server configuration. So we are using Clear Linux, which is optimized for the boot procedure. So I think we can achieve several seconds time scale.
I think we can do better than that, yeah.
Yeah.
So you skipped the firmware by using kexec.
Yeah.
Which, if the fix that you're updating is in the firmware at initialization time, you're therefore not actually running the new code. And likewise, if the fixes that you're trying to get from the update are in the initialization code in the new kernel, that is, say, there's a bug in the initialization of the IOMMU, you're skipping that as well. How do you know if the update you're trying to apply has that the vital parts of it are in the part that you're skipping and therefore won't actually get the fix you need?
I'm not sure I understand your question.
Well, during your reinitialization, you're deliberately skipping a lot of the normal boot process. You're skipping the firmware boot, you're skipping IOMMU initialization, you're skipping certain initializations.
Actually, for IOMMU, it's not just skipping initialization. I think there are some modifications to the IOMMU driver. it will recognize this case and try to initialize from some hardware configurations.
Sure,
so
but
it's not just a skip initialization. I think it makes
sure, but the point is you're bypassing a lot of the usual initialization code for things. And if the fixes that you are trying to get from the system update are in that initialization code, then you've skipped exactly the part of the update that you need. So how do you know when you get an update where the fixes are that you need and whether or not this approach is going to be safe because it has fixes in the places that you're going to skip?
Yes, actually, there are some, there may be some compatibility issue when we boot the new kernel up, because the new kernel actually has a different version than the old kernel. So they may have some changes in, we don't know where, we may not know where the new kernel have changed somewhere. So I think the new kernel may need to aware of such use case, so it can pick up the hardware state.
Okay.
On a similar vein, do you have plans to bake anything in to kind of vet the new kernel that you're loading so that you don't end up with a state where you're trying to pick up fixes in some IO, MMU, and init code, and you don't do that and you burn your whole machine down and you lose a bunch of guests? Or your kernel just simply doesn't boot? So rather than relying on people to know that they shouldn't try and kexec from kernel A to kernel B, having something in kernel A to know that, oh, this is not compatible with me.
Yes, I think the same issue that to some extent the kernel need to be aware of such use case, I think. So the later update of the kernel will need to say make some to have some methods to prepare for such kind of use case.
Do you have plans to do that, though? As opposed to you kexec into the new kernel and then you realize you're hosed?
I think, as you mentioned, this is the most complicated part of the approach, I think, because there may touch a lot of subsystems in the kernel. So I think it depends on how we do it. Maybe, we are still looking at this, how we do it,
Yeah, just a follow-up question on that gentleman asked about the IOMU and the EPT page table mappings. What kind of pass-through device you have tested here?
Networking.
Okay. What's the guest RAM size in terms of the host RAM size?
In our test, we just used a small memory size for the guest.
Yeah, I think if you choose close to the host memory size, you might see the issues that the gentleman just mentioned.
So you mean the IOMU state saving and restoring are dependent on the size of the guest?
Yeah, because when you have IOMU, when you have a device assigned, right, all the memory actually got pinned, right? Then the rest of Linux host memory will be used for the page table reserved, right? Then
yes,
if it's
for the page table, not EPT page table,
Both,
it's,
right?
It's IOMU IO page table.
Yes, but the latter has to be reserved, right?
Yes,
So
but
if you are short of memory,
whatever size your guest have, after you restart, even the normal restart, reboot, you have to use that amount of...
my point is that will increase your chance to stop on those memory. So you might see an issue there. It's better to check that.
I'm not sure.
We can follow up offline.
Okay.
Okay, thank you.
Thank you.